Now we recall this model in which the ratio of the surface area here to the surface area down here is secant of gamma 1 over cosine gamma magnitude of n over n dot k. And this model, in this model, the ratio is the square root of 1 plus fx squared plus fy squared. So we want to reconcile the idea that the ratio is secant of gamma equal 1 over cosine of gamma equals the magnitude of n, and I'm writing that incorrectly. No, I'm not, over n dot k. The ratio is also equal to, well, the ratio of delta S to delta A is just this square root of 1 plus fx squared plus fy squared. Can we reconcile the two? Let's take another quick look at this picture. We see that the vector fy delta yj plus fy delta yk and the vector fx delta xi plus fx delta xk are both in the plane perpendicular to the surface at this point. So their cross product must be normal to the surface. Now I'm not going to include the delta x and the delta y in the vectors of which I'll take the cross product. I'll simply assert that the normal vector equal to fyj, and I'm writing that without thinking. The normal vector is n equal, we'll do it in this order, I plus fx k cross j plus fyk. Now those are just the vectors that we've used down here, except that I've factored out a delta y and discarded it, and out of this vector I factored out a delta x and discarded it. We are in any case familiar from previous work with the fact that the vector I plus fx k and the vector j plus fyk both have the appropriate slope, so both constitute vectors that are tangent to the plane at this point, so their cross product is going to be normal. And we've actually calculated the normal in that manner in previous video clips and in previous problems. So here's our normal vector, and that's easy enough to calculate. I cross j is k, so we're going to get k. We'll write that last. I cross k is j, and something's wrong with my direction there. Hang on a second. I'm not sure what I just said, but we're doing this crossed with this using the distributive law. I cross k is negative j, so that's minus fyj, and k cross j is negative I, so we have fx times negative fx times I plus k. So here's our normal vector. Now if we depict our normal vector as such and our k vector as such, then this angle between the normal vector and the k vector is the angle between the normal to our surface and the normal to our plane region, delta x by delta y, down in the xy plane. So that this angle here is gamma. if we project our normal vector onto the k vector, and this is going to depict a right angle. We don't know what our orientation in 3 dimensions is, but this is a right triangle. Then this projection onto k of our normal vector is going to be just n dot k. Our triangle, and perhaps we think of viewing this triangle now from plane normal to the triangle. Our triangle is going to look like this, where this side is n dot k. It'll have a magnitude equal to the magnitude of n dot k. The hypotenuse is just the normal vector, so its magnitude or its length is the magnitude of n. Gamma is defined to be the angle between the normal vector and the k direction, so that cosine of gamma, being the adjacent side over the opposite side, is magnitude of n dot k over magnitude of n. From this, we immediately get this. I should have magnitudes in my denominator. Now this projection I'm going to consider to be the vector projection. What's the dot product n dot k? The k component of n is just 1, and when we dot that with k, if we dot this vector with k, we just get one. And that is not a vector projection. Please ignore my statement that it was. To get the vector projection, we would then multiply this by the magnitude of, well, by the unit vector in this direction, by k. And now it follows that secant of gamma, which equals magnitude of n divided by the magnitude of n dot k. For this particular calculation of the normal vector, the projection is just 1, so that n dot k is 1, so that this equals magnitude of n over 1, which is just the magnitude of n. And the magnitude of our normal vector is just something we can pretty much just read off here. It's just the sum of the squares of these components. It's going to be 1 for the k component, 1 squared, plus fx squared here, plus fy squared here, confirming that for this choice of the normal vector, our ratio here is equal to the ratio we get here, which reconciles these two expressions and these two pictures. I'll point out that this result doesn't depend on exactly which normal vector we use. Any multiple of this normal vector, any normal vector, will be a multiple of this normal vector, so that whatever the multiple is, that the magnitude of that factor, the magnitude of the multiple we take here, is going to appear in the numerator and in the denominator. So it's going to divide out, so that again, no matter what normal vector we used, had we included our delta x and our delta y with the normal vectors that we used here, it would have all divided out. We would have still gotten the same ratio for magnitude of n over the magnitude of n dot k. the result doesn't in any way depend on the fact that our normal vector in this case had a k component of 1, so that our denominator here coincidentally had a magnitude of 1.